Hello and welcome to Homework 1, Part 3. In this last part of the homework, what we're going to do is look at the exact same problem that we took a look at in Part 2. However, this time, what we're going to do is we're going to install what is known as a proportional control onto the system. So in Part 2, what we did was we had an initial flow rate, steady state flow rate going into the first tank. And all three of the heights were the same. All three of the cross-sectional areas of the holes at the bottom of each tank were the same. But this time what we want to look at is, well, what if we wanted to raise the fluid level of the third tank by something like 10%? Well, what we can do is we can install a proportional controller, which is the simplest type of controller, to essentially change the flow rate going into the tanks so that we can have this fluid level of the third tank reach that 10% increase. So what we want to do is we want to have a set point for the height of our third tank, and we basically can use that to manipulate the flow rates to get us to that set point. So again, this is the simplest type of controller. So what we'll do here is we'll have some set points. So we'll have H3 set point. So maybe this, like I said, I think in this problem we're going to be using an increase of 10%. So I have some set point, and anytime we have the set point being greater than the height of the third tank, we'll want to multiply this by some KC. We'll call this is what's known as a controller gain. And it's basically just a proportionality constant that can help us get to our desired set point. So basically, whenever our set point is greater than the height in the tank, the actual height in the tank, we'll multiply this by some controller gain. And what we also want to add in here is we want to base this off of our initial flow rate. So we're starting at some initial Qn. And if we use this control here, this is what's known as a proportional control, we can get at the needed Qn that can get us to our desired set point, H3, which will be 10% increase from our initial steady state fluid level, H3. So what we can do is we can go ahead and just simply plug this into the code that we had for part 2 of this homework, and we can see how this benefits us. We can get closer to our set point, but what we'll see is that we cannot actually reach the set point in our tank without some weird things happening, which I will show you in Python. So let's go ahead and head into Python.
Okay, so we're back in Python here with the same exact code that we used for part 2 of this homework with the three tanks in series. And we're going to go ahead and install the proportional controller. So what I'm going to go do here is up by our givens, or our known values. I'm going to go ahead and enter in that controller gain, this KC value, or the proportionality constant is the easiest way to think of it, I think. And we'll just go off and start with something like 0.01, start relatively low. And what we can do here is set our set point. So what we're going to do again is we want to increase the height of the third tank by 10%. So do 1.1 times the initial height, initial steady state height. And then what we need to do is manipulate the flow rate in order to help us get to that set point. And what we'll do here is multiply by that proportionality constant, or the controller gain KC, anytime that our set point is below what our actual height is in the fluid tank. So H3 set point minus the actual height in the tank, and our starting basis is our initial flow rate in. So let's go ahead and run this and see what we get for our plot. And so if we go up here, and let me add in a block of code actually. Let's see here. So if you look at H3 and our H3 set point, so what we have here, we actually have an array because I've already run it, but H3 our starting height is 5.096, and our set point here, if we want to raise that by 10%, it'll end up getting to around 5.6. So let's look at our graph here and see if we're getting to 5.6, because ideally we want to hit our set point. If we need our the height in the third tank to be 5.6, ideally we would like it to be 5.6. And if we see here, our steady state looks like right about after 1,000 seconds or so, maybe 1,500 seconds, it looks like we get to steady state. And the height in the third tank and all three of the tanks, because we're in steady state, is 5.35. Now, as you can see here, that's below our set point. And you can also see some oscillations here. And this is just simply because we're multiplying by this proportionality constant here. So it's like overcorrecting. So like you're reading a value, you're reading a value, you're reading a value, then you see, oh, it's wrong. Now you need to correct. And this wiggle here, these oscillations, are essentially the system overcorrecting for us not reaching the set point. So what we can do is change up some KC values here and see how this changes. So let's go like to a really small one, 0.001. And as you can see, less oscillations, so we're not overshooting as much and having to correct for that. But we're much farther away here. It looks like we get to steady state a little before 3,000 seconds. We're much farther away from our set point. So we're only getting to 5.1 and we started at 5.06. So a lower KC value, you're going to correct less, which is a good thing because you don't want to overshoot and have all these oscillations in your process. But you're not going to get to your set point as closely as you would as if you did, like, let's see, what do we have, 0.001? Let's do like 0.003 and see what happens here. So when we did 0.01, we got to 5.35. Here we get to 5.48. But as you see, we have more of these oscillations. And I believe, let's see, so if like our total height tank, I know, I guess in the first homework 1 part 1 we had, we knew the total height of the tank, but here, like, if our total height of the tank is 6 meters, then we're actually overshooting the tank before we can even hit that proportional control to correct it. So this is not good. We can't reach our set point, and if we want to keep raising it, we're probably going to overshoot our tank. Like if we go to 0.05, we have more oscillations. Now we're getting to 5.25, so closer to our set point. But if our tank is 6 meters tall, this is obviously not good. We can't be overshooting our tank. So you kind of have to mess around and play with a proportional controller like this. You can't get it to work. Like if you have a tank that's 10 meters tall and you need it to get to around 5.6, well then maybe we can do like 0.08. And well, if you do this, then it starts overcorrecting and it gets way out of whack. Well, let's say we put it at, let's try 0.06 here. So eventually we'll get to some steady state. I can't even see it here because I only have 5,000 points, but maybe let's go like 10,000. So you get to steady state after a while, and it is a 5.5. So you're getting to your set point, sort of, if you need to get around 5.6. But you're also having these oscillations. So if you can wait 8,000 seconds before you can get close to your set point and have all these oscillations, then a proportional controller will work. But it's just not a very good control to have. So it looks like later on in the course we're going to learn about, or we started learning about them already, but proportional integral controls, PI controls, and also PID loops as well. So, but this is it for homework 1 part 3, just the proportional control. Thank you for watching.